I think you have seen this type of the pattern a lot. So I guess that you may know it's with the oil film on top of the water. Okay. So in the topic here, we want to know how this pattern come out. Okay. So we just want to study about the interference, okay, of the light, and then to form this type of the pattern. But one thing before we talking about this stuff, so let's talk about the physics of the reflection of the light. Okay, for example, okay, compared to a string, if we have rope, okay, and then if one end is fixed, and then if we disturb a loop, okay, to get the pulse wave here, so the pulse wave we move to the right hand side and then reflect to the left hand side. Okay, so you can see that for the incident pulse, right, the displacement is in the upward direction, but then after the reflection the displacement is in the downward direction. So with this we can say that the phase the phase difference between the incident one and the reflected one is 180 degree. So it means that the phase is changed. Okay, for example, if initially the phase of the incident ones equal to the 0 degree, then the phase of the reflected one equal to the 180 degree. So now in this case, it's going to be the same as when we have the light and incident on an interface. For example, if we have the light in the medium of reflective index equal to the n1, and then incident on the interface with the medium of the reflective index equal to the n2, where we have the n1 is less than the n2. Okay, so I just want to emphasize this. If we have the n1 less than the n2, it means that the phase of the reflected wave will change by 180 degrees as well. For example, if initially we have the phase equal to the 0, so after reflection the phase will be shifted to 180 degree. But then on the other hand, okay, so let's look at the rope here again. So if the end of the rope is loose, then you can see that the phase doesn't change. Okay, because the displacement is also in the upward direction, right? The phase doesn't change. It can be compared to this case if we have the light progressing from the n1 to the n2. So when we have the n1 greater than the n2, it means that the phase of the reflecting light will be the same as the phase of the incident light. So okay, if the phase equal to 0, so here the phase equal to the 0 as well. Okay. Actually, we can derive this kind of the density from the Maxwell equation, but it's gonna be beyond your knowledge. Okay, so let me just give you the idea here. Okay, so for the conclusion, for the conclusion, if we have the light from n smaller, okay, and then to the n larger, okay, phase of the reflecting light, okay, shifts by pi or 180 degree. But then on the other hand, if we have the light propagating from the n larger and then to the n smaller, okay, the phase of the reflecting light, okay, doesn't change. Okay, so now we talk about let me move the fixtures, then you can have more space here. Right now we talk about the reflecting light, right? But then how about the reflected light? For example, if we just want to consider the wave reflected to this medium or the wave reflected to this medium, right? you need to keep in mind you need to keep in mind that the phase of the refracted light, okay, does not change. Okay, it doesn't change in both cases here. The one that changes is the phase of the reflecting light. Okay, I mean from the smaller end to the larger end. Okay, so now in this case, let's consider this thin film. Okay, so let's consider this thin film. We have the light wave from the air and then to the film. Okay, and then this will be the air again. Okay, so the air to the film and can be the air again. And then if the thickness of the film equal to the T, and if we have refractive index equal to the N, right? Okay, so let's consider this. So we have the light incident on this interface, right? And then some part will be reflected. And then some part will be refracted to another interface here. So don't forget that if we have the smaller end to the higher end, so it means that the refracted light will bend toward the normal line, okay? If the phase of the incident one equal to the 0 degree, it means that the phase of the reflected one must be equal to the 180 degree, right? Why? Because we have the light floating from the lower end and then to the high end, right? From the smaller end to the larger end. So that's why the phase of the reflecting light shifts by pi. Okay, but then the phase of the refracted one still be equal to the 0, doesn't change. So now at this interface, right, we have the wave reflected, and then some part will be transmitted too. Okay, some part will be transmitted too. So now we have the light reflecting from the high end to the lower end. Okay, so we said that the phase of the reflecting light doesn't change, so it means that it's going to be equal to the 0 degree. Okay, because the phase here doesn't change, because this is 0, so this must be equal to the 0 as well. And then again, the reflected light, we have the same phase, right, equal to the 0 degree as well. So now at this interface, right, the light will come and then some part will be reflect and some part will be refract to the air. So okay, about the this is be the reflected one. Okay, this will be the reflected one. Again, we have from the film and then to the air, right? So from the film to the air, so the phase of reflecting light doesn't change. So the phase here equal to the 0 degree as well. Okay, but I mean this is not what we just want to consider, but what the one that we just want to consider is this one, the light traveling from the film and then to the air. Okay, so we know that the phase of the reflected light doesn't change, so then again the phase equal to the 0 degree. Okay, then if we look at here, okay, if we look at here, it means that we can see the interference between these two light rays. Okay, we can see the interference between these two light rays here. Okay, it means that okay, by the way, I forgot to tell you something, sorry. Actually what we are considering right now is going to be the normal incident. Okay, let's just consider the normal incidence. It means that the light will just come here and reflect, right, something like this. Okay, but I just want to make it clear for you to see, so that's why I just do the oblique incidence. Okay, but sorry, but we need to make the normal incidence here to make our structure simple. So we just want to find the constructive interference. Okay, so let's consider the constructive interference. Then the path difference is equal to, okay, in this case, the path difference between these two light rays equal to this length, right? Equal to this length. So it's going to be equal to the 2t, okay? And then it must be equal to the multiple of the wavelength. But now you can see that if we have lambda to be the wavelength in the air, okay, if we have the lambda here to be the wavelength in the air, it means that the wavelength of the light inside the film here equal to the lambda over the n. Okay, don't forget that if we have the wavelength index equal to the n, lambda must be changed by lambda over n. Okay, we have talked this one already from previous chapter. And then we need to multiply with the number. Okay, but then what is this number? Okay, let's consider this. Usually, when we say that if we have the constructive interference, right, we need to multiply with the m, right? Remember, we talked about this one already here. For the constructive interference, we need to multiply with the m. But this is the different case. Okay, why I say that? Because the phase difference between these two waves equal to the 100 and the 80 degree. It will correspond to the path difference equal to the half of the wavelength, right? It means that if we just want to get the constructive interference, we need to shift this thing by 1/2, okay, by 1/2 or by half of the wavelength. It means that we need to add the 1/2 to this equation, okay, and that's it. So this one we can get the path difference between these two light rays equal to this one for the constructive interference. But then on the other hand, if we just want to get equation for the destructive interference, we have the delta, right, equal to the 2t. This is just the same thing, okay? But we said that, okay, to get the destructive interference, so these two must cancel out to each other. But don't forget that the phase has been shifted by pi already, corresponding to lambda over 2, okay? So then we can get that it's going to be equal to the m and then times the lambda over n, okay? You see, it's just different from what we have done from here. Totally different, okay? Totally different from here. Okay, but don't forget that if you just want to use these two equations, okay, if you just want to use these two equations, it can be applied that, I mean, from the n small and then to the n large and then again to the n small, okay, from n small to the n large and then to the n small. You see, from the n small to the n large and then to the n small. That's why you can use this equation. Okay, so now on the other hand, okay, on the other hand, if you have, okay, from the air to the film, right, and then I don't know, maybe to the glass, let's say to the glass, and we assume that the glass we have the n palm, okay, which is larger than the n. So in this case we have the n small to the n large and then to the n larger, okay, n small to the n large and then to the n larger. So we just want to solve, I mean, to find this, we just want to find this type of this equation, right? Okay, so let's see. We have the light from the smaller end to the larger end. So the reflected light must bending away from the normal line. Okay, yeah, maybe like this one. No. Okay, let me change the incident one. To me, it's smaller angle. Okay, here we have like this, and we have the reflecting light, right? This is 0 and 180 degree. So the reflected light must go to something like this. Okay, and then okay, don't forget that the phase of the reflected light doesn't change. So now, okay, this is the phase, right? So some light will reflect, okay, and then some of the light will be reflect like this. Okay, so this interface, right, from the smaller end to the larger end. So don't forget that the glass here, the end palm, will be larger than the end of the film. So the light traveling from the smaller end and then to the larger end. It means that this light we have the phase changed by 180 degree, right? Okay. But now for the refracted one, the phase doesn't change, so it's equal to the 0 again. So now at this interface, right, if we consider the light that's transmitting through the interface, so we have this one, okay. Then again, the refracting light, the phase doesn't change, so it's equal to the 100 and the 80 degree, okay, because I mean these two must have the same phase, right? Okay, so now you can see that if we observe the light, I mean at this position, we can see the interference between these two light rays, right? And again, these two light rays, we have the same phase, okay, because that's equal to the 100 and the 80 degree. Both of them, we have the same phase here. Then we can have that. So now you can have that. To get the constructive interference, we don't need to shift the path length by half of the lambda anymore, okay? So it means that it's just going to be equal to the m and then times the lambda over n, okay? That's be for the constructive interference. But now for the destructive interference, so we need to shift the path length by half of the lambda. So that's why we need to we need to add the 1/2 and then times the lambda and then over n, okay, and that's it. So don't forget that this is just for the light getting from the smaller end to the large end and then to larger end, okay, to the larger. Okay, from the smaller to large to the larger here. Okay, so this is the thin films that we just want to study. Okay, so let's look at some example here. Maybe this one. Oops, sorry. Okay, number 40 from surveys again. We have a lens, okay, made of the glass. So usually the lens that we talked last chapter, right, previous chapter. So we have index of refractive index of the glass equal to the 1.52. It is coated with a thin film of the what's called MgF2 is the magnesium fluoride, right, equal to the 1.38. This is the refractive index. Okay, let me just write down. We have the 1.38, right, for the refractive index, and we have the 1.52 for the glass, okay, and the air is 1, right? So we have the small n to the large n and then to the larger n. It's going to be this case, okay, it's going to be this case here. The visible light is incident normally on the coated lens as in the picture, okay. So for what minimum value of the T will the reflected light of the wavelength equal to this one in the air, okay. So this is the wavelength in the air, not in the thin film. B missing. We just want to find the minimum value of the T when the reflected light B missing. It means that it's going to be the what destructive interference, right? It's going to be the destructive interference, because we don't want to see the reflected light. It's going to be the destructive interference here, okay. Let's see. For the destructive interference, we have this equation, the 2t equal to the m plus the 1/2 lambda over n. So let's just write down this one, okay. So now for the part A, we have the 2t plus the equal to the m plus the 1/2 and then the lambda over the n, okay. But we know that we just want to find the minimum value of the T. If T is minimum, it means that the m must be minimum as well. So what is the minimum m? The minimum m is equal to 0, right? Just equal to the 0. Then we can just rearrange the equation. So to get that, the minimum T is, okay, so we have the T equal to the lambda over the 4 times the n, right? So don't forget to move these 2 to the right hand side. So the 2 times 2 equal to the 4 here, equal to, okay. So let's just put in a number again. This lambda is the wavelength in the air, okay, equal to this value, the 540 in the unit of nanometer. So let me just put the unit here, and then over 4 times the n, right? What is this n? Now you can see that we have the 3n, but which one should we pick to use, okay? This n will be the one that have that will give the path length difference, right? But now you can see that if we look at this one, the path length difference just occurs inside the film, and then our film is here, right, in the magnesium fluoride, okay. Then we can see that this n must be equal to the 1.38, okay. So don't forget to this one. This n is for the film, equal to the 1.38 here. So then we can just compute, right, and then to get the answer to be the 97.8 nanometer, okay. This is going to be the minimum thickness of the film that we can get, that we can use to minimize the reflected light, okay. Okay, so don't forget that we have the 3 centimeter figure, so that's why we need to use our answer must be the 3 centimeter figure as well. Now for the part B. Okay, now for the part B. Are there other values of the T that will minimize the reflected light at this wavelength, right? That's for sure, okay, because I mean right now we're talking about the m equal to 0, right? But if we have the m equal to 1, equal to 2, equal to 3, we can have the various thickness of the film as well. For example, if we have the m equal to the 1, right? So it means that the T is going to be equal to the 293 nanometer. If we have the m equal to the 2, then we can get the thickness to be equal to the 489 nanometer and etc. Okay, but don't forget that this one is the minimum value of the T to get the minimization, right? But still this can get the minimization as well. Okay, another example. Let me just write down. Okay, if we have this type of the structure, okay, so we have the glass slab, okay, this one and this one, the glass slab, okay, so it's just making some angle here, okay, and we have something that just to make this one incline, and then the thickness of the glass is really large compared to this height, compared to the edge, okay, so the thickness of the glass here is large compared to the edge here, and we have the length of the glass slab equal to the 10 centimeter with the small l, and then we have the incident wavelength equal to the 500 nanometer. If we observe at this end, at this position, okay, so you will see this type of the picture. You will see the fringe here. Okay, you can see this type of the picture. So now the question is, I want to find the distance, okay, the distance between the dark fringe to the dark fringe. Okay, I just want to find the distance between the dark fringe and the dark fringe here. Okay, just the one that I drew to you guys. Okay, just want to find this distance, the dark fringe to the dark fringe. Then again, let's think about this one first. So the thin film, right? So which one we will have as a thin film? So we have the glass and the air. So which one we will have as the thin film? So let's think first. I said that the thickness of the glass is very large. Okay, it means that the light here will not be coherent. Okay, it means that it will not have the interference. Okay, because we said that to get the interference we must have the coherent light. Okay, so it will not be the coherent light anymore, so we don't have the interference. The thin film will occur in the air here. Okay, this will be the air. So let's see that we have the glass, right? We have the high index. So let's say that the phase here equal to 0, and then the light just come from the high index, right, and then to the lower index here. It means that the reflecting light will not have the phase shift. So the phase here equal to 0 degree again, and then the phase of the reflected light will be equal to the 0 degree again. Okay, agree? But now at this interface, right, we have the light just come from the air and then to the glass. So it means that the phase of the reflecting light will be shifted by 180 degree. So this one just to be the 180 degree. So then finally this one we have the phase shift by the 180 degree as well. Okay. Then we just want to observe the disruptive interference, right? Because we just want to find the distance between the adjacent, the dark fringe here. Okay, so you can see we have it's going to be this case. Okay, it's going to be this case for the disruptive interference. Okay, because we have from the film and then to the air, right? From the film to the air, it's going to be the disruptive interference here. So that's why we can get that the 2t equal to the m times lambda over n. Okay, so we can get the 2t equal to the m and then times lambda over the n. Okay, but don't forget that this n, right, this n it must be refractive index of the film, which is in this case it's just equal to the 1. Okay, so we can say that this n just equal to 1, right, of the film, the air film. Okay, but what we just want to find, we just want to find the distance between the dark fringe, right, on the glass here. So you can see that it just give you the x already. Okay, the x is to be the portion of the dark fringe from the edge of the glass here. Okay, so we can just take the ratio. We can say that, okay, if the x right here, and then over the L is the total length of the glass slab, right, is going to be equal to the T, okay, equal to the T, and then over the total height of this triangle equal to the H. Okay, we can use this thing because of we have the right triangle, right, and then we just use the similar triangle here. So that's why the x here compared to the L, and this T compared to the H. Or we can get that the x equal to the L over the H, and then times the T. But then what we just want to find, we just want to find the distance between the adjacent dark fringe. So we just want to find delta x. Okay, we just want to find delta x equal to, okay, so the L is constant, the H is constant, and the T will be vary along the x, right? So we can get that delta x equal to the L over H, and then times delta T. We need to find delta T first. Okay, we need to find the delta T first. We can find delta T from this equation. Okay, we said that delta T right, is going to be equal to, okay, the m plus 1 lambda over 2. No, let me just write this way. Is equal to the T at the order of m plus 1, and then minus the T order m. Okay, equal to the m plus 1 and then lambda over 2, right, and then minus the m lambda over 2. So then equal to lambda over 2. This will be over T. Now we can just plug in this delta T into this equation. So then we can get that the delta x here is going to be equal to the L over the H, right, and then times the lambda over the 2. So now let's just plug in the number. The L is the 10.0 times 10 to the negative 2, and the wavelength is the 500 nanometer. We have the H is 0.0200 times 10 to the negative 3, and then times the 2. So then finally we have delta x equal to the 1.25 millimeter. Okay, so this gonna be our answers. Oops. Okay, so it's gonna be this distance over delta x.